So many thanks to Nick for the welcome, and welcome from me as well. So I'm actually going to start off with a little bit of history, some really ancient history. Well, AI today, leading up to today. So the artificial intelligence as a field really was inaugurated at this conference way back in 1956, the Dartmouth conference. And the proposal for that conference was written by John McCarthy, Marvin Minsky, Rochester, and Claude Shannon of information theory fame. And the proposal was written in 1955, and it's a remarkable read. I recommend that you have a little look at this. The proposal itself is only 4 pages long or so. And this is how it starts. It says, "We propose that a 2-month, 10-man," he meant person, but it was 1955, a 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves." This is a great sentence. "We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer." So we're still working on that one. But the remarkable thing about it is that in the rest of the proposal, he sort of anticipates a lot of the paradigms of AI that are still, and a lot of the challenges and problems that are still important today. But one of the things about it that I think is very interesting is that what motivated the founders of the field back in the 1950s is that they wanted to create what we now call artificial general intelligence. So they wanted to create machines or endow computers with the kind of intelligence that humans have to solve a huge variety of problems, or to learn to solve a huge variety of problems. And one of the things I want to emphasize in this little talk is the difference between that ambition and the kind of AI that is actually around today, which is mostly specialist AI, working at it. So we have a general purpose technology, but it's usually applied and engineered for very specific applications. Okay, so another little bit of history. So now thinking more about how this ambition of AI was then picked up, and then picked up by industry and academia, really with kind of particular applications in mind, then, well, we've gone through this series of cycles of hype and disappointment. So after there were some early successes following the inauguration of the field, and that led to a great deal of excitement, so we had a kind of big period of hype. But then there was the so-called first AI winter. So there was a certain amount of negative assessment of progress that had been made, and the funding dried up, the interest dried up. You couldn't get tenure as a professor in this area anymore. So we had this AI winter in the 1970s. Then there was a huge amount of investment from Japan in the so-called fifth generation project, a huge amount of investment, which had a knock-on effect. You had investment from Europe and America as well. So another big cycle of hype. But then that really didn't kind of live up to expectations. So there was another trough, the so-called second AI winter. But then along came the 2012 ImageNet competition, where Jeff Hinton's team put in this deep learning entry, which absolutely kind of swept the board and showed that neural network-based machine learning was capable of doing image recognition with this big data set of fairly natural kinds of images. And that was a really big, important moment. And that's what's led us to where we are now, which is really on this upturn of a lot of hype. So by one of my lab rules is that nobody is ever allowed to present a graph that doesn't have clearly labeled axes. And when I first prepared this, so I realized that my y-axis wasn't labeled at all. So what the hell do you put on the y-axis for all this stuff? So it's like something like scientific credibility, media interest, investment. All of these things follow this kind of cyclical pattern. Okay, so what's led to all of this excitement? Well, it really is all about neural networks. So like this is my 5-minute tutorial on neural networks. See if I can get it out in 5 minutes. So the idea is that in neural networks, so all of the systems that we're interested in at the moment that are leading to all of this hype, or the majority of them, are based on this idea of a very simple artificial neuron unit, which is a unit which takes the weighted sum of all its inputs and produces an output, and it's then followed by a non-linearity. And we connect all of these neurons together into a network, and the networks are usually organized in layers, in feed-forward layers. So we have an input layer, and that feeds into a number of hidden layers. Here there's only one, but in a deep network there will be many of these hidden layers, and then to an output layer. And what learning is all about is about taking, we might be interested in, for example, training our system to recognize handwritten digits. So this is the MNIST data set, which is one of the classic data sets that's used, in kind of machine learning 101 in any course. So the idea is that you present a digit into the input layer of the neurons, and then it computes its output, and then it labels this digit. And depending upon how it labels the digit, it might be right or it might be wrong. Now let's assume that it's wrong. In that case, you work out a whole set of gradients that can update all of the weights. So you remember that the neuron it computes a weighted sum, and it updates all of the weights in the network to make it a little bit closer to getting the right answer for that particular example. And then you do that thousands and hundreds of thousands of times. With MNIST, maybe 100,000 times, and then you'll be able to. Then you'll have a network that can correctly label brand new images. If you're doing something like ImageNet, which is where you want to recognize and label more naturalistic images of dogs and faces and cats and cars and so on, then you might need many millions of examples. But using that technique, you can build neural networks that have an enormous number of applications. So, for example, recognizing and labeling images. And really, the key to the success of the recent success, there are three things. And the two main things are the availability of very large amounts of training data. And it turns out that these kinds of networks are very successful if you have a very, very large quantity of data to pump through them. So if you train on huge data sets, then they're very successful. But in order to train on very large data sets, you need an awful lot of compute. So that's the second thing that sort of led to a huge amount of progress, was the availability of a large amount of compute power, which was really driven by the availability of GPUs, graphics processing units, that could be repurposed for the kind of parallel computing which is just right for these kinds of neural networks. So that combination of lots of data, the computing power to process all of that data, and then the third thing is a number of algorithmic innovations, but they really weren't kind of the main thing. That combination suddenly led to neural networks being very powerful tools and able to learn things, not just simple kind of benchmark things like MNIST in the lab, but things that have practical application for industry. So that's one of the sort of big. This kind of learning is called supervised learning, because it's supervised in the sense that you are providing a certain input, and when you're training it what the output you want it to supply is. So the data is labeled in that sense. Now, a second very important class of learning problems is so-called reinforcement learning. And reinforcement learning is basically learning by trial and error. So it's the kind of thing that we all do if we're learning, for example, to play tennis or something. If we haven't played much before, then we practice. We try out different things. We see what works and what doesn't work. And so based on the kind of how successful we are, the reward signal that we get, then we'll repeat the action that gave rise to a reward, a positive reward, and we'll avoid actions that gave rise to kind of negative reward that failed. And so that kind of learning by trial and error is called reinforcement learning. So in the context of robotics, for example, we might want to build robots that learn how to grasp things, for example, in an industrial setting, and that do so by trial and error. They might try out lots of possibilities until they get better and better at that. And one of the big advances that happened in 20 around 2014 was the idea of combining these two ideas, the deep learning, deep neural network-based deep learning with reinforcement learning. And the idea there is that what you do is you take one of these deep neural networks and you put that as the component in the middle of this deep learning agent, and you make that the component that is learning how to map actions to how to map inputs to actions that will lead to an accumulation of reward over time. So that idea of deep reinforcement learning, so that was really came from DeepMind, which is the company I work for 80% of the time at the moment. And that idea has turned out to be very powerful, and I'm sure that you are aware of its application, for example, in the game of Go, where the DeepMind team were able to show that it could beat the world's greatest Go players, and now it can completely wipe the floor with even the earlier versions of itself. It's now sort of way better at. Prior to that, video games, so you can use deep reinforcement learning to learn a whole suite of these Atari video games where all the system takes as its input is just the raw pixels on the screen, and it has no idea that there are objects or that there are walls or anything like that. It just takes the raw pixels and the score as its input, and through trial and error, it learns to get a better and better and better score at the game. Those are signs of good progress, and the robotics, the kind of grasping example, learning to grasp example I used earlier on, is the sort of application where you see deep reinforcement learning in robotics. Now, this is kind of great progress in artificial intelligence, but now I want to just kind of hark back to the original ambition of the founders of the field to create an AI which has the same kind of general purpose intelligence that we humans have, because we haven't really got there yet, and it's very important to understand that ambition of achieving that kind of artificial general intelligence is really quite a way off. And by the way, I should say that point out that when they were talking about it back in the 50s, they just used the term artificial intelligence to talk about what we now tend to refer to as artificial general intelligence. But because AI is used these days very much just for talking about very narrow application areas, we've had to rebrand the whole ambition of creating that kind of general intelligence. So people use the term artificial general intelligence for that goal. So with that larger goal in mind, we can identify a number of shortcomings of, for example, deep reinforcement learning, which is at the forefront of attempts to kind of get to that holy grail of AGI. Here's a little list of some of its shortcomings. So the deep reinforcement learning and deep learning in general is very, very data hungry indeed. And in fact, you'll all be very much aware that everybody says that if you want to do AI, then you need data. And all the companies that are kind of pushing and using AI in a big way are, they're going to be successful at it to the extent that they have access to large quantities of data. But if we think about human intelligence, in fact, we get away with making very, very smart decisions on very little data often, very little data. Quite a lot of past accumulated experience, but we might be presented with a new problem that we've never seen before, and we're often able to solve that with very little data indeed. And if you watch DeepMind's agent learning to play those Atari video games, then you realize that it's actually taking such a long time. It spends hours and hours just jittering around with something like Space Invaders, just jittering around on the screen, doing nothing at all, and you think, oh, it's really actually a bit stupid. It's, it hasn't figured out that there's the basic idea of the game, which any child will figure out in about a minute flat. So this kind of data inefficiency is a shortcoming of today's deep learning. And then there are related things. So it also, there are various aspects of higher level cognition that it's not so great at. And so one particularly important one is transfer learning. So transfer learning is where we acquire expertise in one domain, and we are able to use that expertise in a very different domain. I mean, when we get a university degree, then, you might take a very vocational degree, but a lot of what you're learning is how to learn new things and how to problem solve in kind of new domains. And humans are very, very good at that kind of transfer learning, taking experience you've acquired in one class of problems and applying it in a very different class of problems. So that kind of transfer learning is another thing that deep learning is not very good at. And another issue which is very important, particularly for certain application areas, is that neural networks are, I had to put in the word somewhat, because they're not completely opaque, and you can do all kinds of techniques to try to visualize exactly how neural networks work. But the truth is that often a trained neural network will be working in a way where you can't figure out exactly why it's taken the decision that it's taken. So there is no humanly comprehensible chain of reasons that you can interrogate and check that led to the decision that it's taken, whether, for example, whether a particular image contains a cat or a dog or a person or whatever. Okay, so that leads to, so I don't know how am I doing for time? 10 minutes? Okay, excellent. Okay, so now I just want to talk a little bit about this goal of achieving general intelligence. So today's AI technology, that kind of deep learning technology, for example, and other AI technologies, they do certainly have many, many applications, and we can list the sectors in which we can find applications for this technology and where it's potentially can revolutionize some of these areas. Manufacturing, scientific discovery, transport, healthcare, marketing, they're all areas where AI and machine learning are making a huge impact. But the AI systems that we deploy in all these sectors are specialists. So we really need to put together a new system for each new application. So usually we have to engineer the architecture for a particular application. We have to carefully engineer the training pipeline. We have to retrain it with vast amounts of data again. So each application is kind of a separate thing. But a general intelligence, like a human being, is able to perform a really wide range of tasks. And as I've already emphasized, that was the original aim of the field, to achieve artificial general intelligence. So what do I think are so the title of the talk was Obstacles to Artificial General Intelligence. So I better say something about obstacles to artificial general intelligence. So of course, nobody at the moment knows how to achieve artificial general intelligence, but there are plenty of people who are working on it, and there's a kind of renewed enthusiasm for the prospect that we might succeed. And so my personal list of important topics that need to be worked on, or problems that need to be cracked, is this. So common sense, abstract concepts, and creativity. So the first thing, one of the biggest challenges, I think, is to endow computers with a common sense understanding of the ordinary, everyday world. So an understanding of the everyday world of people and things and the consequences of ordinary actions. So, I mean, just starting off with the understanding that we all have that there is a world out there, an enduring world with objects that persist, and lots of solid objects that have certain kind of fundamental common sense properties, like you can't pass through them. There are lots of, they're made up of surfaces that are can't be penetrated. Things interact in certain ways that we understand. One of my favorite examples is the concept of a container. So we all have this concept of a container. So if we look around the room, we'll find many, many containers. There are jugs and cups and bags, and inside my rucksack down there, you'll find other containers. It's kind of got pockets, and there are pockets in the pockets, and inside there might be a box with indigestion tablets in it, and then even that itself you can break down into little parts. And this notion of a container is an incredibly general purpose concept that we apply all the time in all kinds of settings. And it has some fundamental properties. So it has kind of a contents, it has a boundary, it has ways that things can move in and out of the container. And we can use this common sense concept in all kinds of settings, and we do. This room is a container, the contents are ourselves, there are certain portals for getting in and out of it, and ways of moving contents in and out. We can think of the city as a container. We can think of many more abstract things as containers. So there are folders on my laptop, which I think of as containers. You can think of a bank account as a kind of container for money, where money goes in and out, and mostly out. So that's just one example of a very, very basic, fundamental, common sense concept that we all have, and we can apply in very, very different, new. We could apply that in a very novel kind of setting. So computers currently lack that kind of common sense understanding of the world. So they're not able to conceptualize the world in these sorts of basic terms. And I think that's one of the fundamental kind of shortcomings. And it's very related to this second one, which is abstract concepts. So I gave an example. So the container is actually a very abstract concept. We can apply it in very specific and concrete settings, such as that of a cup and so on. But as I showed, we can apply that concept in much more abstract settings, like the bank account and so on. And then finally, creativity. So this is what I characterize it as the productive yet open-ended propensity to try out new actions. Now, a reinforcement learning agent of the kind that we've seen has to try out new actions, but the truth is it's really not very creative. When it's trying out new actions, mostly it's just sort of random stuff. Whereas if you look at a child, any sort of young child in a play setting does an extraordinary number of creative things, just playing with toys, interacting with other children, making drawings and pictures and Lego and that kind of thing. So that kind of way of exploring the world, there's actually quite a lot of structure there in all of the randomness, and endowing computers with the ability to explore their world in that kind of way is very important as well. So that's my favorite 3 list of obstacles to AI. I'm actually going to skip the next slide. Well, actually, no, I won't skip it. So one of the themes that I'm working on to try and move towards this, and I'm working on this theme both in DeepMind and in Imperial, in a way that can be siloed from each other, of course, for legal purposes, is the combination of symbolic and neural artificial intelligence. So it would take a little while to kind of unpack that idea, but basically one of the paradigms for AI that was inaugurated by John McCarthy and others way back in the 50s was the so-called symbolic paradigm, which is all about constructing representations of the world expressed in language-like formalisms. And then using logic-like rules for manipulating them. Now that is very out of fashion these days, and that's very much not the way that neural networks work. But one way to try and bridge the gap to artificial general intelligence is to rehabilitate some of those ideas from symbolic artificial intelligence, and that's one of the themes that I'm particularly interested in. Okay, so I've got 2 more slides. I've given a similar presentation a couple of times where I have 3 slides and the 3 at the end. And one is like, why build AGI? When will it happen? And will it destroy us all? So I'm going to omit the will it destroy us all one because I'm so fed up with that topic. But you're going to get the other 2 slides. So why build artificial general intelligence? And what's the reason for building it? And basically, the problem is that all of our current AI systems, I think this discussion of common sense exemplifies this, they really lack a true understanding of the world and what it contains. And so like a medical diagnosis system, it doesn't know what a person is. It doesn't know what disease in general is. It doesn't know that there are actual objects out in the world that include persons that can live and die and suffer and so on. And an autonomous vehicle doesn't know what a car is. It doesn't, as I say, it doesn't know that there's a world out there. There's no meaningful sense in which it has that very basic kind of understanding which was required for an artificial general intelligence. And general intelligence goes hand in hand with that kind of true understanding. And essentially, in every domain where we apply AI today, if we had AGI, then it would be more capable and more robust. And applying AGI to a new domain wouldn't require engineering everything completely from scratch. It might require the AGI to do a bit of self-guided learning, but it would, in the same way that we humans do, but it wouldn't require a team of engineers to build the application. And AGI would be able to make connections across domains unlike today's specialist AI. So there are many, many very compelling reasons to investigate the artificial general intelligence. So then this is the question that I always get from journalists who interview me about this stuff, apart from the will it destroy us all question. The other one I always get is, when's it going to happen? And the answer is, I have no idea. This is an enormous, difficult challenge. And nobody knows how to do this. And nobody knows when it will happen. So any dates that you hear are completely speculative. And if somebody names a date and they turn out to be right, then they were just lucky. So nobody really knows. And the reason nobody really knows is because I think we need a number of conceptual breakthroughs to get to AGI. But we don't know how many conceptual breakthroughs we even need. We don't know how many there are. And we don't know, what the intervals are going to be between these conceptual breakthroughs. And while there are periods when you have a conceptual breakthrough, so let's say that winning the ImageNet, it wasn't really a conceptual breakthrough, it was kind of breakthrough. Then we had a period of steady progress, and you can kind of measure that. But what we don't know is when the next big breakthrough is going to happen. So, unknown intervals between breakthroughs, unknown number of conceptual breakthroughs needed to get there. So basically we have no idea when it's going to happen, but if it does, it will have a significant impact. So I'll stop there. Thank you very much.